Have you ever stopped to think about how a computer actually understands your code? I mean, it's one thing to spot a typo, but to grasp the actual meaning behind the commands, that's a whole other level. And that's exactly what we're diving into today.
So to kick things off, I've got a little puzzle for you. Just a simple question. Look at the sentence that's about to pop up. Is it grammatically correct?
The apple ate John. Let's break it down, right? You've got a subject, the apple, a verb, ate, an object, John. All the pieces of the puzzle seem to be in the right spots.
So yeah, it follows every single rule in the grammar book. But it's just nonsense, isn't it? The meaning is completely broken. Well, and this is the cool part. Programming languages work the exact same way. You can write code that has perfect grammar, but is just logically absurd.
Okay, so here's our game plan. We're going to see how a compiler tells the difference between grammar and meaning. We'll peek inside the compiler itself, figure out what this meaning check is all about, see some real-world examples, and then wrap up with why this is all so incredibly important.
All right, first things first. We really need to nail down the difference between an error in your code's structure versus an error in its logic. They are two totally different beasts.
Over on the left, we've got syntactic errors. You can just think of these as basic grammar mistakes. A missing semicolon, a bracket that was never closed. The compiler just throws its hands up because it can't even figure out the shape of what you wrote. But on the right, that's where it gets interesting. Semantic errors. Here, the grammar is flawless, but the meaning is just off. The classic example? Trying to add the number 5 to the word cat. The structure is fine, but the idea itself makes no sense.
So this meaning check, where does it actually happen? Well, it's a very specific step in a much bigger journey your code goes on.
See, your code doesn't just run. It gets processed in a bunch of different phases by this program called a compiler. And understanding that assembly line is really the key here.
So it all starts with lexical analysis. This phase just chops your code up into individual words, or, as they're called, tokens. Then those tokens get passed to the syntax analysis phase, which is basically the grammar checker. It arranges everything into a structure, a kind of sentence diagram for code. And then finally, we get to our star player, semantic analysis. It takes that perfectly built structure and asks the most important question. Okay, this looks nice, but does it actually mean anything?
And this diagram here shows that flow perfectly. You see your source code go in, it gets turned into tokens, those tokens are built into that parse tree, and bam, right there, the semantic analyzer steps in to check that tree for any logical inconsistencies. It's the gatekeeper of meaning.
Okay, let's zoom in on this semantic analyzer. What exactly is it doing? What's its job? Well, the official definition says it's the phase that checks for semantic consistency. Really, its one and only mission is to make sure every single thing you've written is meaningful and plays by the rules of that specific programming language.
I love this analogy. Think of it like a detective. It takes the structure of your program, the evidence, and it cross-references it with a list of all the known facts, which is called a symbol table. This table is just a running list of every variable, every function, what type of data it holds, and where it's allowed to be.
So what's on this detective's checklist? Oh, it's very thorough. It's doing type checking, making sure you're not trying to mix numbers and text inappropriately. It's looking for undeclared variables. You can't use something you haven't introduced. It's checking scope. Are you trying to use a local secret in a public space? And of course, it checks every time you call a function to make sure you gave it the right info.
All right, enough theory. Let's see this detective in action.
One of the absolute most common things the semantic analyzer sniffs out is what's called a type mismatch.
So look at this. We're telling the computer, I'm creating a variable called x, and it's going to hold a whole number, an integer. But then we immediately try to stuff the word hello into it. The grammar is perfect, but the analyzer's type checker goes, whoa, hold on, that doesn't make any sense. And by catching it right here, it saves us from absolute chaos later on.
Now here's where it gets really cool. The analyzer isn't just about pointing out what's wrong. It can actually be a problem solver and make smart little adjustments on the fly.
Check this out. The code wants to multiply x, which is a decimal number, by the whole number 30. Now, to avoid an error, the semantic analyzer does this clever thing called type coercion. It just automatically converts the integer 30 into the decimal 30.0 right before the multiplication happens. It's a tiny, invisible fix that makes the whole operation valid. Pretty smart, right? So let's bring it all home. Why does any of this matter? Why is this phase so unbelievably critical for pretty much anyone who writes or even uses software?
Well, the payoff is just massive. For starters, it catches these logical bugs before your program is even built, which is way easier than finding them in the wild. And you know those super helpful real-time error messages you see in your code editor? The ones that underline the problem and tell you exactly what's wrong? That's all powered by semantic analysis. It just leads to better, safer, more reliable code all around.
I saw one source put it this way, and I think it's perfect. Semantic analysis is the compiler's last line of defense. It's that final, critical checkpoint that makes sure a program isn't just grammatically correct, but that it's also logically sane.
But, and this is a really important but, we have to remember its limits. The semantic analyzer is an absolute master of the language's rules. It makes sure your code follows the letter of the law. What it can't do is read your mind. It has no idea what you, the programmer, actually wanted the code to do.
And that leaves us with one final big question to chew on. If a compiler has gotten so smart that it can check for meaning, what is the one kind of meaning that it can probably never, ever truly understand?